a while since Wednesday. It always does for some reason. But this is what we ended with. So we looked at a formula. So we were given a chemical formula, and then we just broke it down into percentages. So this is called percent composition. So if you're asked this on the exam, you just take each atom present in the formula, and then you multiply it times the number of atoms. So here, iron, we had 2. We had 3 sulfurs and 12 oxygens. And then we found the formula weight of the iron 3 sulfate. Okay, so that was the big key here. You had to find that 399.9, or otherwise all your numbers would be off. So when you add all these up, you get a percentage. That means out of 100, so we times by 100. You should get 100% because your total percent composition should be 100 at the end. So if you don't, then somewhere you messed up. Okay. For this example, we're given the formula, okay? But what do people do if they don't know what the compound is? Okay, so what do you think they would have to do? If you extracted some compound or discovered or found or made a compound, but you don't really know what the formula is, what do you think you would have to do? You'd probably have to go to the lab, right? And you'd have to experimentally figure this out. Okay, so that's what I'm going to show you next. So I'm going to show you in a second. First, I'm going to tell you the difference in 2 formulas that we'd be trying to find. And then we're going to talk about how you can find this experimentally. So it's one experimental way that you can find this. Okay, but first, we want to talk about the difference in empirical formula and molecular formula. Okay. Personally, molecular formula is a lot more useful, and that's what you're going to see 9 times out of 10 must be on a chemical reagent bottle in the lab. Okay? The molecular formula is the true formula. It's exactly how many atoms you have of each element and in what order and everything. So if you look here at molecular formula, so ethene, pentene, hydrogen peroxide, their formula, if you were to draw the Lewis structure or whatnot, is H2O2, C5H10, C2H4. That's all of the atoms present in that compound. Okay, empirical formula, okay, we're going to find this, but we're going to use it to help us find the molecular formula. So it is important. It's just not, if I came up to you and I said, the empirical formula of the compound you need to find in the lab is OH. Well, guess what? There's about 100 compounds in the lab that have an OH group, so it doesn't really help you without knowing specifically what the formula is. Okay, but an empirical formula is the simplest, the smallest whole ratio of atoms present in a compound. Okay, so if we look at all 3 of these right here, okay, we have C2H4. Okay, is that the simplest formula for ethene? Can we divide by a small whole number ratio? Okay. So if we were to take C2H4, what would our empirical formula be? CH2, exactly. And what about for pentene? It'd be the same, right? So this is kind of showing you why it's not really that useful to just know the empirical formula, because ethene and pentene are 2 totally different compounds, but their empirical formula is the same. Okay, you just divide by that small whole number ratio. So CH2 would be the empirical formula for ethene and also for pentene. Okay, so if we had C6H12, what's it going to be? What's its empirical formula? CH2. Okay, so if you tell me, go find CH2 in the lab, then probably going to be able to find 4 or 5 different things, I mean, depending on how big the lab is. So that's not really that useful. But we can find empirical formulas, and then that helps us find the molecular formula. Okay, so you'll see this here in a few minutes. But does everybody see the difference between those 2? Okay, so your molecular is exactly how many atoms in that ratio that you have. Okay, H2O, that's already in its simplest form, right? You have 2 hydrogens and 1 oxygen, so you can't divide those numbers by anything else other than 1. So it would be your empirical as well as your molecular formula. Okay, so if we want to find formulas, so we have the compound, we don't know what it is. We don't know the formula. Okay, so like I said, last week we did percentages based on a formula that we knew. Okay, but we don't know that now. So we want to try to find the percent composition experimentally first. Okay, so one way that you can do this, okay, is by combustion analysis. So there's kind of an explanation here. I'm just going to hit the high points. This is used oftentimes for hydrocarbons. Okay, so you can take, any kind of hydrocarbons, just carbon and hydrogen, and you can put it into a furnace or some kind of heated vessel here. And when you stream in oxygen and heat it, just like if you take methane and you stream in oxygen and you light it on fire, okay, it's going to combust, right? So you essentially take your sample and you combust it. Okay, that's why it's called combustion analysis. And then you have these absorbers, okay, and then you read how much water was absorbed and how much CO2 was absorbed. Okay, one equation that you're going to have to know, which Chapter 3 will go over it more and more, but if you have methane plus oxygen, that yields CO2 plus water. It's a combustion reaction, so it's really the only reaction that I have you know. Like if I tell you, CH2 reacts with oxygen, you should be able to write it out. Okay, but we'll see that in Chapter 3 and practice that. Okay, so we get these masses of water and CO2, because that's what forms when you combust a hydrocarbon. And you take those percentages, and then you can find out the formula. Okay, so the whole point is we're not real sure what was in here, what this sample was. We take a small amount, we combust it, and then we see what percentages of water and CO2 were absorbed. Okay, this is one way, and this is the way we teach in Chem 111. However, do you think this might be a little bit dangerous? Hence the word combustion. Yeah. So this is used still today, okay, but it's not a practice that we would ever do in an academic setting. Okay, so you do see it in industry some, but they're trying to go more away from this. So we're using different types of instruments that can detect. One's called nuclear magnetic resonance. It's a very expensive instrument. I would love to have one here, but I don't think I ever will in my lifetime see one here. But that's what I use all through my research, and so your larger institutes will have one. But you put your sample in, there's no combustion really involved at all. Okay, so it's a lot safer. Okay, but this still is, used today, so we still talk about it some. But it can be dangerous. Okay, first thing, we're going to find the empirical formula. All right, and I told you a lot of times we can find it first, and then it'll help us find the molecular formula, because that's really what we want to know, right? We want to know how many atoms exactly are in our formula. Okay, but oftentimes, just like H2O, our empirical formula can also be our molecular formula. There's no more that we need to simplify it. Okay, first thing you may want to make note, because this is something that's just often missed and forgotten. Everybody seems to get it in class, and then they see it on a homework or an exam, and they just forget. Okay, we're given that a compound has 24.74% potassium, and you can read the rest of those percentages. Okay, a percentage is always out of what? What number? 100. Okay, so we can actually consider this here out of 100 grams of a sample, right? So really, we know, based on that percentage, we know there's 24.74 grams, okay? So just circle that percentage and write out equals grams. It's the same thing, because if we look at it out of 100 grams, those percentages can be used for that, okay? All right, so we did this experiment. All right, so we had an experiment, we combusted a sample, and we read those percentages. Okay, so we found there's 24% potassium, 35 manganese, and about 40.5 oxygen. Okay, so we now know that those could be our grams. So to find the formula, what you're going to do is convert from grams to moles for each percentage. Okay, so we did this last week. Okay, so don't look too far down. It looks like a whole lot, but it's really not bad. So we take our percentage. Okay, we said earlier this is equal to grams. To get from grams to moles, we divide by the grams of whatever the atom is or element that we're looking at. Okay, so where did I get that 39.10? Where does that number come from? Periodic table. So you can go ahead, before class even starts, have your periodic table out every class because we'll be using it. Okay, so and whenever we look at the periodic table and we get a mass, how many moles is it out of? 1, always, right? We haven't seen anything over 1 at this point, okay? So we divide. We divide so that our units cancel, and we get moles. 0.6327 moles potassium. Okay, notice it's manganese, not magnesium, so be careful on that one. Okay, if we divide by 54.94 grams per mole, I get this off of the periodic table, then I get moles of manganese. Okay, so I take each mass, it was a percentage, and I just go to moles for each one. Okay, I do the same for oxygen, and I get 2.531. Okay, so these are my resulting moles here. Okay, so if I did this in the lab and I had my percentages from my experiment, I would then convert to moles for each of those percentages. Okay, I can give you this, don't be confused either. I could give it to you in grams. I could say you found 24.74 grams, either way. Okay, just recognize that both work the same. Okay, then you're going to just take the smallest number, which you have two that are exactly the same, right? Okay, so it doesn't matter which one you use, but you're going to divide by the smallest number. Okay, so the smallest number of moles. So if we divide by the smallest number here, we get 1. We have the same exact number here, so we get 1. And if we divide 2.531 by 0.6327, we get 4. Found the moles, and then divide by the smallest number. Okay, if you had 5 atoms here, you would still take the smallest number and divide it into all of the moles. Okay, now we have the number of moles or atoms in our formula. So we have 1 potassium, 1 manganese, and 4 oxygen. Okay, this is an example where this is potassium permanganate is what this is called. Okay, this is an example where the empirical formula is the same as the molecular. So that is exactly how many atoms that's in potassium permanganate. Okay, so we don't have to do or go any further here. Okay. All right, this time you're given grams. Works the same way. Okay. You just have cobalt and oxygen, so you just have 2 atoms. So you're going to have to convert each to moles and then divide by the smallest number. I'll go ahead and give you a hint. You're going to run into a little issue, and that's okay. That's why I want you to do it first and then see how you might run into a problem. Okay? And the problem is just going to be where it doesn't quite work out to being a whole number. Okay? And I'm going to show you how to fix that. Okay, so do the first part, convert grams to moles. I have cobalt and oxygen. Okay, and then when you divide by the smallest number, I want you to stop there. Everybody have their moles, grams to moles? Okay. All right, did you divide by the smallest number? Okay. And what happened? Anybody run into a problem? Okay, you got 1, and then what did you get? Okay, and then 1.33 or something like that. Okay, so the last problem, it worked out pretty perfectly, right? We got just whole numbers, no problem there. Okay, so you can fix this. It's not hard to do. Okay, so if that happens, so this is where you are right here. You got that 0.1110, and you always divide by 1 and got 1, and then you got about 1.333. Okay, so what I do, I have to get that 1.333 to a whole number. So if I take 1.33 times 2, do you get a whole number? Now, what do you get? 2.66. Okay, so that didn't work. All right, what if I take 1.33 times 3? Then you get what? 3.99999. Right. If you get into that 9, that is plenty close enough to 4. Okay, it may not be. 0.6 is not close enough, but if you get to the 0.9s, you can go ahead and round up. Okay, so if you get a number where it's a fraction, you're going to multiply it times whatever number you need to give you a whole number. Okay, but if you multiply this times 3, that means you said you had 3 times 1.33 oxygen, so you have 4. Okay, but if you do that to the oxygen, you also have to do that to the cobalt as well. Okay, so you would just take that 1 times 3, and so you get cobalt for 3, oxygen 4. Okay, questions? Okay, just don't forget to do it also to the other atom that's present. And there won't be a lot of these. Most times I'll set you up where it'll work out and be a whole number and you don't have to do that. Okay, but if you run into that problem, that's how you fix it. Okay, we were asked for empirical formula. So like I said, these are the steps you go through. We're not really, we didn't get asked for molecular formula. All right, the reason we learned to find empirical formula first is because you can do this exact thing and then one more step and find a molecular formula if you're asked. So I teach it this way. Some students see it differently as they're studying and come up with their own little way, and that's fine, okay, as long as you show your work and whatnot. But the reason I teach it this way is because if you can do this, then you can get a lot of points on your exam, okay, because there's only one step left for a molecular formula. So instead of missing the whole problem and doing it totally different, you can at least get, 6, 7 points out of 10 if you just miss the last step. Okay, so it's easier to teach it where it builds on each other. Okay, so if we look at this, okay, we're given a compound. Of course, we're trying to find the formula, so that's not given to us. We're given a percentage, so it's 85% carbon and 14% hydrogen. Okay, be sure you write out how many ever significant digits are there. Okay. Something different here is that I'm given the molar mass. Okay, so what's the molar mass? What does that mean? Okay, very good. 56.1 what? Grams per mole. So what does that mean? What's molar mass different from anything from last week? Molar mass, we're in units of grams per mole, right? Okay, and it's when you add up all the masses of the atoms in the formula and you get the total mass, right? Okay. We want to know now the molecular formula. Okay, so what you're going to do, you're going to do the same thing. So I want you to find the empirical formula first. So take your percentages, which are grams, right? It's out of 100, and find moles for carbon and hydrogen. Then divide by the smallest number and come up with your empirical formula. Okay, so do that first. I'll kind of do it with you as you're going here. Everybody get CH2? The empirical formula? Okay, any questions on how I got this? No. Okay. What's the molar mass of CH2? Okay, CH2. If you add up the molar mass of CH2, what is it? Okay. So it's going to be about 14.03. Okay. So the formula you just found, that CH2, that simplest whole number ratio formula, right? Okay. If you add up that molar mass, it's 14, which in our problem, the molar mass of this compound is 56. Okay, so we're not done yet, right? We haven't accounted for a lot of the mass of this compound. Okay? So if you divide 56.1, which is what we know our molar mass is, by 14, whoa, I don't know what just happened there. Sorry, something just... No idea what happened. Hang on. Made it really big to see. Okay. So if you divide 14 into 56, what do you get? 3.9999, which is basically 4, right? So our molecule is 4 times the size of CH2. So all we do is take our empirical times 4, and we get C4H8. Now if you add up the molar mass of C4H8, it's 56.1 grams per mole. Okay, so you find empirical, and then you add up the molar mass of the empirical and compare it. And you just divide here by what's given. So I have to give you this molar mass, or otherwise you can't, keep going and find it. And if you get 4, or whatever that number is, then you have to multiply it through the number of atoms for your empirical formula to get your molecular formula. Yes? Well, it can. It's the simplest form. So like if you looked at C4H8 and you divided by 4, because you can divide both of these by 4, right? You would get CH2. So that was the empirical, but it doesn't give us really enough information. It's really useless in a lab because, like I said, there's a million compounds that have CH2 that could be broken down to that. Maybe not a million. That'd be a little stretch. But this is what's important, okay? But we can find this first by finding empirical and then using our molar mass to find this. So it is important for us to know how to find it, but we use it a further step usually to find the molecular. Yeah. What I did, but I didn't. There we go. Okay. This is just another interpretation of chemical formulas, and we don't not do a whole lot on this, but it is kind of a segue into what we're about to do in Chapter 3. So don't get bogged down with this if it's a little much for you right now, because you'll start learning to do more than one-step, two-step conversions. But this problem wants to know what's the mass of phosphorus in ammonium phosphate. Okay, so if you look at it there, we just have 1 atom of phosphorus, right, in our formula. Okay, and so we just want to know what's the mass of the phosphorus if we had 45.3 grams of this compound. So how much of it is just phosphorus? So the first thing we would do is we would take our grams of what we know, right? We know 45.3 grams ammonium phosphate, okay? And we would add up the molar mass. So we would take 3 nitrogens, 12 hydrogens, 1 phosphorus, 4 oxygens. So I encourage you when you're at home studying to do that. Make sure you get 149.09. And we know that if we add up our molar mass, it's always out of 1 mole. So first step is just to convert from grams to moles. And our units will cancel. Okay, this next step, so imagine that, I didn't have enough room, but imagine this is, just up here. It doesn't have to be down there. We have 1 mole of ammonium phosphate on top, so our units down here in the denominator have to be mole ammonium phosphate. Okay, when it's written like this, and we're given grams, and it's really just understood that we have, 1 mole of this. It's not a very pretty one there, but that's a 1. Okay. And then in our formula, we only have 1 phosphorus, right? So we say we have a 1 mole of our total compound to 1 mole phosphorus. And this is called a mole-to-mole ratio. So we have a 1-to-1 ratio. Okay. Now our units, so this would cancel. Our units are in moles of phosphorus now. Okay. And so the last step here is in 1 mole of phosphorus, because it's always out of 1 when we go find the mass of phosphorus, is 30.97. Okay, and so everything cancels. Okay, the key here is to keep everything lined up so units cancel. And this was kind of our key step. It was our mole-to-mole ratio. Okay, and then moles cancel, grams on top, and you end up. So out of that 45.3 grams, 9.41 were grams of phosphorus. Okay, we'll do lots more of these this week and into even next week where they're similar. We start using more and more steps. So if you're not quite clear on this, it'll probably clear up as we do more practice. All right, the last thing in Chapter 2 that we're going to cover, and it's not a huge section in your book, but I feel it's important just because you have to think about this when you're in the lab, and it's called the purity of a sample. Okay, so if you go into a lab, and I encourage you to look at your reagent bottles when we use things, a lot of times it's going to say on the bottle 98% pure, or 98.2% pure, 99% pure. Okay, that means that the whole sample is not completely pure and not exactly what it should be, okay? Which means the other percentage is an impurity. Okay, and this just happens. So as much as chemists try to come up with new methodologies with all kinds of things, it's almost impossible to get 100% purity, okay, in any chemical reagent. Okay, so we have to account for that, because if 2 grams of my bottle is impure, it's not going to react the way that it's supposed to react, right? So it's pretty much useless in that bottle. Okay, and so we have to take this into account. Okay, so percent purity, once again, is a percentage, and it's part over whole. What's the mass of the pure substance over the mass of the total sample times 100? Okay, so it's part over whole times 100. The mass of the total sample includes impurities. Okay, so what we want to find is what's pure. What of a certain mass is 100% the compound that we want, or that we're about to add to our flask to do chemistry. Okay. So once again, if you look here, we have a bottle of sodium phosphate. We've got this in the lab, and on that bottle, it says it's 98.3% pure. Which, sounds pretty good, right? Okay, but the larger quantity you use, that little percentage that's impure becomes important. Okay, so we need to know how much is not pure. Okay, so if we have 98.3%, we can once again consider that to be out of 100, right? So 98.3 grams of sodium phosphate out of 100 is pure, okay? 98.3 out of 100, because that's what a percentage is, right? Some reason this doesn't always click with students, okay? So we have in 100 grams, 98.3 grams will be pure, okay, because that's the percentage that's on our bottle. So if we have 250 gram sample, so it's a pretty large amount, maybe not for industry, but for academic setting, that's pretty big amount. We wouldn't have any of you measuring 250 grams of anything in our lab. And if we put our unit conversion, here it is, we would set it up. This is our gram sample including impurities, right? Okay, so I have 250 grams of this sample that's 98.3% pure. So we know that 98.3 is out of 100. So our gram samples cancel each other. 250 times 98.3 is 246. So out of 250 grams, 246 grams of sodium phosphate is pure, meaning that's going to react the way that you want it to. Okay? So 4 grams, if it's 250 minus 246, 4 grams of that bottle is impure. Okay? All right, any questions on chapter 2? No, not necessarily. No, it could have been, so we could have had, 98.6%. There's all kinds of different percentages. So, no. Occasionally, things that are very simple structures, easy to make, even this, this is a salt. It's going to be, you might even find this 99% pure, and you can't even find 99.9% pure on simple salts and things. And so really, you don't even have to account for it then because that's such a small percentage. Okay, but you can also find 95% or, 94. All right, we're going to start chapter 3 and then hopefully have time to work some problems. If I can find chapter 3. Not too many things on my... Okay. Chapter 2 basically just prepares us for chapter 3. Okay, we've learned to convert from grams to moles and moles to grams of the same compound. You've also used Avogadro's number, so can't forget about that. So we've thrown that in there. And when we use Avogadro's number, we found molecules, atoms, or particles. Okay. Now we're going to look at what chemistry is really all about. It's about chemical equations, taking two things, reacting them together, and forming new products. That's what chemists want to do, and hopefully they can do this efficiently and good yield and, be very, very productive. Okay, so the first thing we have to establish today is what's an equation. So what is that? What are we reacting? What's going on? So we're going to do that first. And then we're going to look at something called balancing equations. So some of you, if you've had chemistry before, you've probably done that. And then we'll probably stop there. But later this week, you will learn how to finish your lab. Okay, so you kept one of your labs last week so that we could understand the calculations. Okay, so it wouldn't even be a bad idea, maybe even Wednesday, to bring it because you can probably go ahead and finish it when you're in here. All right, so our goal today, which we're not going to get to all this by any means, is to know what a chemical equation is and to be able to balance it. So we're not even going to get to the other calculations today. Okay, we'll save that for Wednesday. Okay. A chemical equation is basically a representation that we can write on paper to the best of our ability that shows us reactants, which are going to be on the left side, and products, which is what we are hoping to form. And then we also are going to have what we call coefficients. Okay, these numbers are the numbers out in front of the chemical name. I'll show you those in a second. And this tells us the relative amounts of our products and reactants. Okay, so if we look here, I'm trying to kind of show you on a molecular level as well. Okay, so these are just kind of ball and stick models. Okay, but here's this one reaction I told you you're going to have to know. So you have methane plus oxygen. Okay, notice there is a 2 right here. That's a coefficient that's out front. Okay. Yields CO2, carbon dioxide, plus water. And it also has a 2 out front. Okay, in order for this reaction to occur, okay, a lot of things go on, and we don't talk about all of it in Chem 111. Okay? We look at mostly the big picture. We have reactants, they react, and they form products. Okay, but in order for this to happen, there has to be energy. These molecules have to collide with each other, and not just collide, they have to collide in the proper orientation so that bonds will break and new bonds will form. Okay, so really we've rearranged our carbon molecule and our oxygen molecule and now formed 2 totally different compounds, CO2 and water. Okay, and also, because you have this 2 out front, how many molecules of O2 do you have? 2. Okay, you have a 2 out in front of water, so you have 2 molecules of water. Okay, so just to reiterate this, we're going to use this reaction over and over just because it's easier for us not to have to keep adding up molar masses. Once we do it once, we can be done. Okay, so we have one formula unit. Okay, if we look out, it's an understood 1 out in front of that iron 3 oxide. Okay, that means we have 1 mole. That's very important. Okay, that coefficient represents the moles. And then if we add up Fe2O3, we're going to use this number here in a few minutes, so you may want to write it down. It's 159.7 grams per mole. Okay. We have 3 molecules of CO. So we would have 3 molecules, meaning we have 3 moles. We have 2 iron atoms, so we have 2 moles. And then 3 CO2, that's our product. I need to reiterate this again. Reactants are on the left. They react and collide to yield. That's when we draw a reaction arrow. Okay, if you even look at the word that says yield or form, to form, that means you're drawing your reaction arrow there. Okay, and then we have 2 atoms, iron, and 3 CO2 molecules. So we have 3 moles CO2. Does anybody know what that little triangle is, a little delta sign there? Change. But what do you think it means here? Yeah, kind of think that. Yeah, it means heat. Yeah, so you're heating. This involves heat. Okay, so you won't see that, all the time. It depends on the reaction. Okay. We stated the law of conservation of mass way back in chapter 1. Okay? And we're going to use it here and show you what this means on a chemical level or an equation level. Okay, the law of conservation of matter says that there's no detectable change in the quantity of matter, okay, in a chemical reaction. So this means that our chemical equation has to be balanced. We can't lose or gain mass in a chemical equation. if we start with 8 carbons in our reactants, then we have to yield 8 carbons. Okay, it doesn't mean they have to be in the same arrangement. You know, we started with methane and we formed CO2. Okay, but we have to have as many carbons or as many hydrogens or whatever the elements are on either side of a reaction equation. Okay. All right, so I want you to look at this and try to answer this question. Okay, how many carbon atoms, hydrogen atoms, and oxygen atoms do you have on each side of the equation? Okay, meaning each side means left side, reactant side, right side, product side. Okay, and then try to determine, is this reaction balanced? Okay, so we have 3 atoms involved, carbon, hydrogen, and oxygen. Okay, if we look over here, how many carbon atoms do we have? 3. Okay, if we look over here, how many do we have? 3, yeah, because it's an understood 1 right there. Okay, next is hydrogen. We have 8, and we have 8. 4 times 2 is 8. Okay, we have 10 oxygen. Here we have how many? 6 plus 4. Okay, that coefficient that's out front multiplies through the subscript for each atom in that compound following the coefficient. Okay, so it's understood 1 there. So we have 4 plus 6. All right, so if we looked at our both sides of the equation, do we have the same number of atoms on each side? Yes, this is a balanced equation. This comes from your little key terms sheet I told you last week for chapter 2 and 3. I made you a key terms kind of outline that you can use when you're studying, going through, highlight points, that kind of thing. This comes from it because this really, to me, is the best way to kind of talk about, kind of give rules for balancing equations. Okay, so you just looked at an equation and you said it was balanced, which that's the first best step. That's great. Okay, but you're going to have to take an unbalanced equation and balance it yourself. Okay, so we need to provide some guidelines of how to do this. Okay, so a chemical equation, I've got what it is again up here. Okay, we have our reactants and they form our products, and they have to have the same number of atoms on each side. Okay, so there's our starred thing there. All right, where did I write? Let me see. Where is it? Okay, here we go. To balance equations, you adjust the coefficient. Do not ever change a subscript. Okay? If you change a subscript, you just change the total compound, right? Okay, this reaction forms CO2. If you change that to a 4, that's not CO2 anymore. That's CO4. Has a different Lewis structure, and you just change the whole reaction, which is wrong. Okay? You can only change these numbers out front. Okay, so here's a 2. That's a coefficient. That 2 out front is a coefficient. And these are understood to have 1. Okay? And once again, this is the reaction that you have to know. So if I was to write in words, methane reacts with oxygen, write the equation. You would have to write this. Okay? And we'll show, of course, how to get the 2's there in a minute. Okay, this is the system I use for balancing. I find that it works the best. Okay, but I will tell you, balancing equations, some of them are simple and take, 60 seconds or less. Some of them are trial and error, and it takes time. So you have to practice them, and you have to adjust things. I will say, if you've spent more than 5 minutes changing numbers and going back and forth, you probably missed something somewhere, so you might just want to erase it and start over. Okay, because sometimes you start changing and changing. You're not accounting for the oxygens. You only are looking at those on accident. You forgot to count these over here. Okay, so you might just want to start over and try again. What I do is I balance all atoms that are present besides oxygen and hydrogen. Okay, that's where I start. Okay, so here, all I have is carbon, right, other than hydrogen and oxygen. Okay, and I'm telling you, this will help you. Okay, it gives you a good basis, and probably 7 times out of 10, it saves you some extra work and just peace of mind, not to have to sit there and change things 100 times. Okay, then balance hydrogen and then oxygen. Okay, not all chemical equations have hydrogen and oxygen in them, so you're not, if they don't have hydrogen and oxygen, then you can't balance it, right? Okay, but for situations where you have hydrogen and oxygen, balance everything else, then hydrogen, then oxygen. So you need to get that in your mind. If you do oxygen first and then hydrogen, you're probably going to add yourself some more work, okay? Because usually if you set the number of hydrogens, you've also helped set the number of oxygens, okay? So here we go. Let's do these together. First thing I do, students do different things. Some like to keep kind of a list underneath each side. I have 2 carbons on this side, so write out carbon, I have 2. And then hydrogen, I have 6. A common mistake is to accidentally add up atoms from one compound and forget that you have also that same atom in another compound. So like this, you have an oxygen over here with the C2H6, but you also have oxygen O2. Okay, so you have to add up. It's all of those atoms on the left side and on the right. Okay, so if we look here, we have C2. We have 2 carbons on the left. Bless you. But how many carbons do we have on the right? 1. Okay, so what can we do to change this? How can we fix this? Bless you. We can add 2 as a coefficient. Exactly. So let's do that. There we go. Okay. All right. Now are we going to go to hydrogen or are we going to go to oxygen next? Hydrogen. Okay. How many hydrogens do I have? Hydrogens. On the left side. Sorry. 6. Okay. And on the right, I have 2. What can I multiply by to give me 6? Perfect. Okay. Oxygen is left. Okay. So if I look over on the left side, how many oxygens do I have on the reactant side? I only have 3. All right. What about on the right? I have 2 times 2, right? I have 4 plus 3 times 1, 7. Okay? All right, I need how many more oxygens here? Right. All right. So what could I do to change this? So more than likely, I want to try to manipulate this oxygen, okay? Not this one, because if I change the coefficient out in front of it, then I also change the numbers of carbons and hydrogens, and then you're back at square one, trying to do the whole thing over again. Okay, so what number can I put there that'll give me 7 total on that side? Right, so if I put a 3 here, now I have 3 times 2 is 6, plus 1 is 7. Perfect. Okay. For the next one, so the answers are just down here with those arrows, but I haven't shown them yet. What atom am I going to start with? Yes. I will also say that here you have rubidium, oxygen, hydrogen, and you have a sulfur. So technically you could start at rubidium or sulfur, right? My personal experience, I always start with just like when I'm reading from left to right, I start with the first atom on the left that I see. That's where I start, okay? And sometimes that will help. Okay, if we have 1 rubidium and 2 on the right, what are we going to have to do to the left? Not a subscript. Coefficient, yep. Okay. All right, we look at sulfur. How many sulfurs do we have on each side? 1 and 1, right? So leave it alone. Okay, now we're going to go to hydrogen. How many hydrogens do we have on the left? 2, and how many do we have on the right? 2. Leave it alone. How many oxygens do we have on the left? 1, 2, 3, 4 is what I heard. Okay, we've got 4. Everybody see that? Everybody agree with 4? Okay, how many do we have on the right? 4. Okay, this is an example. If you started wrong, not really wrong, but if you started with oxygen or hydrogen, you would have ended up doing extra work just to find that all you needed was a 2. Okay, so I would follow the order. You can make it harder for yourself if you want to, or you see it better that way, that's fine. But this scenario is an example where it helps, okay, to start with that first atom. So there's our answers. Okay, and just don't forget, we had oxygens both places here. It's a total amount of the atoms to be balanced. Okay, this is an example. I'm going to show you this. But if I had said methane burns in oxygen to form carbon dioxide and water, you would need to be able to write that equation out. Okay, but since it's a little different, it's propane, or excuse me, it's heptane here. Okay, there you go. So now you want to balance it. So add up your number of atoms, adjust your coefficients, and balance. And then at the end, you can always check your answer. Yeah, that'd be an example. This one is really easy because you're just putting in methane with C7H16. But since I told you your only one you have to memorize would be the methane one. So this one I would technically give to you. But if I said methane reacts with oxygen to form, I may not even tell you what the products are. You would have to know methane plus 2O2 yields CO2 plus 2H2O. So that's the equation you have to know. Yeah, but for this one, more than likely, I'd go ahead and just give you the equation like I did right there. Give you another minute to do this one. This one will look like you've already got it. Okay, so if you start with carbon, you had 7, so you had to add a 7 over here. Does everybody get that far at least? Okay. All right. Then which atom do we go to? Hydrogen or oxygen? Hydrogen. So we've got 16 Okay. And then originally, so we would have not had the 8 there, so we added an 8 so that we would get 16 on the right. Okay, if you add up your oxygens here, you have 7 times 14 plus 8, so you have 22 oxygens, so you need an 11 here, because 11 times 2 is 22. Did that go too fast? Everybody get that? Raise your hand now, because I can go back and do it again if you have a question. Okay. All right, this one, like I said, I like for you to see when you might run into a problem, okay, instead of just telling you what problem you're going to run into. Like earlier, okay, we did that percent composition and found that we had a fraction and needed to adjust. This is the same kind of thing. You're going to hit a problem, okay, so I want you to see it. So let me write this out. So I would give you, here's your equation. So ammonia burns in oxygen. Okay. Whoops. Okay. It's not going to erase, so. Okay, so try to balance this equation. The ones we've done so far have been pretty straightforward. This one will have to do a little more adjusting. Do what? Okay, so they don't always work out perfect, but this one you kind of hit an issue. Give you a couple minutes to see what you come up with and see what you can figure out, and we'll go over it together. Anybody hit a problem? Not? No? Depends on if you know how to fix it. Then it's not a problem. Okay, if I start with hydrogen, I have one on each side originally, so it's not always going to be perfect. We're probably going to have to adjust that nitrogen, but for right now we have one on each side, so we leave it alone. And then we go to hydrogen. Okay, so we've got 3 on the left, and we've got 2 on the right on the product side. Okay, so what are we going to have to do here to get these to equal? Yeah, we're going to have to make it a 6. That's the only way. So we're going to put a 2 here and a 3 here. Okay. when we put that 2 in front of the ammonia, what did we also change? Yeah, the number of nitrogens. So we have to go back over here and put a 2 there. Okay, so this is kind of just a scenario. You got to kind of go back and forth. Doesn't always play out perfect. Okay, did everybody get that far? Okay, good. All right, now let's add up. Let's check real quick. So I always kind of check as I'm going. I've got 2 nitrogens on each side. Perfect. I've got 6 hydrogens, and I've got 6. Okay, so now I've got to get my oxygens matched up. All right, so if I look over here right now, all I've got is 2. Okay. If I look over here, I have how many? Okay. All right, so which side am I going to need to adjust? The left-hand side. Okay. Well, if I put a 2 there, that gives me what? 4. But if I put a 3 there, it gives me 6. Okay, so this is an example where I need an odd number, right? But my formula tells me I always have to multiply times 2, which is going to give me an even number. Okay, so did anybody run into this? Okay, what did you do to fix it? Okay, somebody said they changed water to 6. Who said that? Okay, why'd you do that? To an even number. Yeah. Okay, but when she changed water, she also had to change everything else, right? Okay, there's 2 ways to write this. I really accept both, but I like the way that Darby just said, where you basically what you do is you double everything. Okay? So let me just show you this first, though. So if we need 5, right, and we know there's no way we can get that with a whole number, so we could use a fraction. What times 2 equals 5? 2.5, right? So if we take 5, that's the number that we want, and 5 halves, so you can almost think about it like these 2's cancel each other. 5 halves, 5 divided by 2 is what? 2.5. So 2.5 times 2 equals 5. And that's what we need, right? Okay, so that's a fraction. Or the best way is to double everything. So meaning, when I say everything, I mean coefficients. Remember, we can't change subscripts. So if we double, okay. All right, now if we take 5 halves and we double it, what do we get? 5. So we get 5, 4, and 6. Okay. The issue was not that we didn't know how to balance or we didn't know how many oxygens we needed. The issue came from the subscript. Okay, so if you run into an issue where you need an odd number and no matter what you do, you can't get an odd number, then that means you need to write it as a fraction or double it, and that will give you the correct answer. Okay, there's lots of practice. Be sure that you are, I want to make some announcements to be sure everybody knows when everything's due. Okay, you've still got some time, but go ahead and be sure you're starting your homework. So your Unit 2 homework is due October 13th, and that seems like a while away, but it's really not. So it's 2 weeks, and we're going to keep covering more and more, so be sure you're doing your homework. Also, the worksheets online on Blackboard, what can you turn those in for? For extra credit. When is the extra credit due? The class before the exam, so on the same day that your homework is due on OWL, so on the 13th. You have to do all of the problems, and you need to do them regardless, even if you don't get them done by Monday, because they are great practice. So that's just more practice. So you can start the worksheet, the homework, and the worksheets that are online. So there's great balancing questions, molar mass, grams to moles. So please get started on those. But have a good morning off from lab, and I will see you Wednesday. Have a good day.